In our many different lectures, we have covered many different types of chemical equilibria. We have, covered acid-base equilibria, solubility-product equilibria, complexometric equilibria, redox equilibria, and then lastly, we're gonna cover the last type of chemical equilibria, called phase distribution equilibria. And hopefully you're gonna see all chemistry out there. It's all based on many of these different equilibria. So lastly, we're gonna talk about phase distribution equilibria. And as the slide shows, phase distribution equilibria is the basis of analytical separations. So in this chapter or in this lecture, I'm gonna introduce you to analytical separations. And the learning outcome that I hope you're gonna achieve out of this chapter is to understand the theory behind chromatography based on distribution equilibrium. Also, hopefully, you're gonna learn about the different types of chromatography, their components, and of course, their principal applications as well. And hopefully, you're also gonna learn how to classify analytical separations based on mechanisms, but also based on the components, particularly the mobile phase that is involved. Traditionally, analytical separations, started in form of solvent extraction. And I think all of us have had a bit of experience with solvent extraction, or what we would refer to as liquid-liquid extraction. In this case, I'm calling it liquid-liquid chromatography, which is the basis, of instrumental type of chromatography that we do in the lab. So the theory that we use for instrumentation as far as chromatography is concerned was actually derived, from the very traditional mode of doing analyte extraction using solvents. And this is where you take, for example, an aqueous solvent, and the sample is in the aqueous solvent, and you want it, to be extracted into an organic solvent just using a separation funnel, and you just shake it up, and hopefully the analyte migrates, to the organic phase. Now, there are many applications of these sort of primitive sort of technique. Now, if you think about analytical doing separation, or trying to get matrices out of an analyte so that you can do analysis. So that's one major reason why we do liquid-liquid extraction, to remove matrices, from the sample so that we can easily analyze it without matrix interferences. But other important, applications of this theory of liquid-liquid extraction actually is in pharmaceutical, what you call pharmacokinetics, in terms of drug distribution in the body. Now, most of the drugs, are fairly hydrophobic, and you get them into a body which has got a combination of an aqueous and organic phases. Our bodies are made up of fat, which is hydrophobic, but they're also made up of, lots of water, the blood, which is a solvent sort of that distributes most of the drug. Drug is involved in distribution, between phases, the fat, organic phase, as well as, the liquid phase or the aqueous phase, which is the blood in this case. So for pharmacokinetics, drug distribution in the body, again, this very simple, type of equilibria is relevant in that case. Or even in environmental contaminant mobilization, how environmental contaminants distribute in the environment. It's another major application, of this type of theory. So the K, in this case is what you refer to as partition equilibrium. And as I've said, the analyte, partitions between the aqueous phase, which is the phase 1, and it migrates, to the phase 2, which is the organic phase. And the relative, distribution of the concentration of the analyte in the organic phase divided by the analyte remaining in the aqueous phase is what you refer to as the partition coefficient, the K in this case. So how do you determine if you have completely, extracted the analyte into the organic phase? We use this kind of very simple relationship, where Q refers to the fraction of the analyte, that remains in the aqueous phase, whereas obviously 1 minus Q would be the fraction that partitions, in the organic phase. And the extraction efficiency, to see how well we are doing, you just take 1 minus Q, multiplied by 100. And of course, if you get 100%, that means, your extraction efficiency is very, very good. If you substitute what I've just talked about, into the partition coefficient up here, you actually get, this relationship. So these are the number of moles of the or the concentration rather, of the analyte that is in the organic phase, and you can see, this is a concentration, of the analyte, that is in the aqueous phase. And if you make Q the subject of the formula, you can see that you get this relationship here, where V1 is a volume that you use to do the extraction. V1, again, volume used to do the extraction. K is a partition coefficient. And, V2, in this case, would be the volume of the organic phase. So hopefully you can see, how we arrived, at this situation. V1, is the aqueous phase, and V2, is a solvent in the organic phase. Now, this relationship shows you when you actually do one extraction. So this is the fraction that remains in the aqueous solution when you just do one single extraction in your separation funnel. Now, in most cases, you're gonna see that you need to do more than one extraction to improve the extraction efficiency. So that's one extraction, but often you need to do multiple extractions. And so if you want to determine the extraction efficiency, you just need, to have this relationship to the root of that number. So the n here refers to the number of extractions. So which is preferable then? Look at this problem here. Is it better, to do one single extraction with the same volume of the organic phase? Or is it better to actually do multiple extractions with small volumes, of the organic phase that eventually equates, to the total volume, in this case, when you're doing a single extraction? Now, I'd like you guys to do these at home. You just need to substitute, these numbers into those equations. And you're gonna see in A, where you just do one big extraction using volume V2 as 500. And of course, V1 in this case is 200. You're gonna see you get an extraction efficiency, of about, 90%. So the fraction that will be remaining is gonna be, 10%. Whereas if you did multiple extractions where n is equals to 5, and V2 in this case is equals to 100, and V1 is equals to 200, you're gonna see that you've got extraction efficiency of close to 100%. So just do these at home, and you're gonna realize that when you're trying to do an extraction, it is better to do small volumes of your organic solvent, and you do multiple times, for the extraction. So you actually get a better extraction, and you do multiple times small volumes of the organic solvent. I hope that is clear. Very important theory, that goes into the practice, of doing extractions. Now, until now, you can see our extraction efficiency equation here is based on these thing that I'm calling partition coefficient. But you're going to realize that life is not as simple as that. Sometimes you've got compounds that actually change their form, when you dissolve them in water. And of course, we've already done this. If you take a weak acid or a weak base, or even you take a complexometric reagent, if you dissolve them in water, we all know that, for example, for weak bases, they tend to hydrolyze in water. So actually the form of that compound keeps changing, in the aqueous environment. And as such, when that is happening, the extraction efficiency should be calculated as follows. So instead of using K, in that case, we should use D. So distribution coefficient is normally used, when you've got a solute that changes its form or that undergoes chemical equilibrium, resulting into different species in the aqueous environment. So in that case, you actually do not use a K, but you use the distribution coefficient or the D. So take note of the difference between the D and the K, the partition coefficient. Let me just remind you very quickly, about the theory of this. If you take an acid, conjugate acid, such as that, we know it undergoes dissociation to give you that. We already know the equilibrium expression is going to be that, And so the D, the distribution coefficient, would be equals to the compound, that is in the organic phase, the B, divided by the B, which is in the aqueous phase. So very similar, really, to the partition coefficient. But take note of this. Some of the B, has been protonated, to give you that. Now, any charged species is much more soluble in an aqueous phase. All right. So if at all you've got a charged species, it prefers to be in an aqueous phase. And that's why, you're saying in the aqueous phase, we have the B as well as, the protonated form of B. In the organic phase, we have the neutral B. Okay. And then you can see the partition coefficient, on the other hand, it ignored, these BH plus because we assume no protonation is taking place when you're doing partition coefficient. And so you're going to realize actually this D is proportional to K, and the proportionality constant, is what you refer to as fractional composition, the alpha, okay? Now remember, alpha is what you actually do as the 5% rule. Remember, when you do the 5% rule, that is what you refer to as a fractional dissociation, all right? And that's what you refer to as that. Now, when you're dealing with a conjugate base, okay, and it's going to get clear in the next slide, the fractional composition is actually defined, by this relationship. The Ka divided by this proton, plus the acid dissociation. Okay, so take note of that relationship. It's going to get clear in the next slide for sure. Let me give you an example of a weak acid. A weak acid undergoes hydrolysis. That one is fairly familiar. The equilibrium expression is equal to, the concentration of the products divided by the concentration of the reactants. The distribution coefficient, would be equal to whatever is in the organic phase, which is the HA. It has to be neutral, divided by the HA, which is in the aqueous phase, But we know HA also forms a conjugate base, and this one is charged. Remember, every charged species prefer to be in the aqueous phase, and so it's going to partition there. K, on the other hand, the partition coefficient assumes no dissociation is taking place, and so it's going to be equals to the HA in the organic phase, HA in the aqueous phase. And so we know that the fractional composition, HA, is actually equals to this relationship here. And I'm going to show you that possibly in the next slide. In fact, it's right there. And you can see it's just by basic, substitution, right? You can see just by basic substitution that I arrived at this relationship where the fractional composition, okay? And this refers, to the composition of the HA that is present in that form and that has not dissociated. It has not dissociated, okay? So take note of that. So the fractional composition of HA is actually equals to this relationship, and you can see how I've derived it right there. And so actually the distribution coefficient then, and you can see I've derived it right there, is equals to this relationship multiplied, by the K, which I have, in that relationship there. And so I hope you're able now to see how I arrived at this relationship if you see my working, on the right-hand side here. Okay. So hopefully it's clear the relationship between the D distribution coefficient and the proportionality constant, which is actually, as I've said, really the 5% rule. The 5% rule. The fraction of HA that is present in that form divided by the formal concentration, which is a combination of HA plus A minus, which is the other form that is actually present. So let me take you through how you do extracting, of weak acids and bases into an organic solvent. Okay. So the way you do this, because as I've said, weak acids tend to get dissociated, bases tend, to hydrolyze. The way you do it is you use the pH. So you need low pH when you're extracting weak acids, maybe something like aspirin. All right. So you need to convert. You need a low pH, so that you convert all the A minus into the HA because it's gonna get protonated. As we've said, the HA prefers to be in the organic phase because it is neutral. So you want it to be neutral. And so in that case, again, you want the D to be large. If you go back here and take note of this relationship, if the hydronium concentration, is fairly high, then my D is gonna be fairly high. And so in that case, then I'm gonna be extracting, most of my analyte into the organic phase. Okay. So if at all you've got a weak acid, the approach, to extract most of the organic acid is to make sure the pH is very low so that all the analyte is protonated and as such it is neutral and it's gonna prefer to be in the organic phase. On the other hand, if at all I've got a weak base that I'm trying to extract from water into an organic phase, so something like cocaine, all right? Cocaine is a weak base. And so in that case, I need a fairly high pH, so that so that I can convert, all the conjugate acid here, into the base. Okay. So that this one is fairly neutral, and again, it's gonna prefer to be in the organic phase. I hope that's clear. So you're extracting the weak acid, low pH, so that all of it, is protonated. If at all you're dealing with a weak base, you want high pH, so that all of it is deprotonated. Remember, this is deprotonated. All right. So how about you solve this problem at home where you've got now a weak base and it has a partition coefficient of 8.5, favoring to be in the benzene organic phase of our water. And you've been given, the KB in this case to be 1.6. And so you've been asked, to calculate the percent that got extracted, when the pH is at 4 and the pH is at 11. And essentially, all what you need to do is evoke this relationship, remembering that the D, or the distribution coefficient, is equals to the partition coefficient multiplied by the fractional composition here. And the definition of the fractional composition here, we already saw it, in the previous slide is this. And so that's the hydronium ion, the pH factor, that's the Ka, which you've already been given up here. And so confirm you get the answers as follows. So answer for the pH of 4 is 0.1%. And for the pH 11, confirm it's around 94%. Again, just by evoking, those numbers into the equation that I've given. Hope it's fairly clear. So what would be the procedure to separate a neutral solute? Assume I've got a neutral solute and I also have a weak acid, that is present, in that sample, okay? So my sample is a mixture. I've got a neutral solute. Maybe I'm going to call S as maybe dextromethorphan. That's a good example. A cough syrup. Dextromethorphan, whereas HA possibly is an acid, such as aspirin. Okay? And my interest is to actually separate both of them because they are very important, pharmaceutical products. I want to separate both of them into an organic solvent. So how do I do it? Now, remembering, of course, HA, tends to dissociate. And if it dissociates, then it doesn't extract very well because it becomes a charged species. So the process would be as follows. Step 1, I would add a strong base so that I convert, my HA, to the A minus. And if at all I convert it to A minus, it will prefer to be in the aqueous solution. So it wouldn't be able to be extracted to the organic phase. And so step 2, I would add an organic solvent so that now I can extract the S, leaving the A behind in the aqueous solvent. And so now I've got my organic solvent that has already extracted the S. So that one is already complete. Now, and then number 3, I would add a strong acid so that I convert, these A minus back to the HA through protonation. So it becomes neutral. See, it becomes neutral. When it becomes neutral, now it's easier to extract it into an organic solvent because it's not charged. Any charged species, again, prefers to be in an aqueous environment. And so after this now, I'm going to add a fresh solvent of organic phase, which now extracts HA, to the organic phase. And now I've resolved both my neutral solute and, my weak acid. I hope it's clear to see the process. A very practical problem, in the industry, where you've got one neutral compound and the other one is a weak acid or a weak base. And both are important and they need to be resolved. How about you do this problem at home, which is just analogous, to what I have up there. So finally, I'd like to sort of very quickly, take you through, and I think I've already said it, how I'm getting, these fractional compositions so that you're familiar, with the derivations, of these equations. Again, I've got an acid, such as this. I've already said, the fractional composition really refers to the 5% rule, which is a concentration of HA in its neutral form divided by the formal concentration, before any dissociation happened. We know the formal concentration is equal to the combination of HA and the A minus, right? So the total concentration, of HA and the A minus. And you can see then, using this equilibrium expression, I can substitute, these one right there. And equally, I can substitute F, which is equals to HA plus A minus. And then I can substitute these right there. And you can see when I do that, finally, and you can follow these one, my fractional composition, the 5% rule here is equals to that, which is what I obtained earlier. If at all I had, a conjugate base, just follow the same process and you're gonna see the fractional composition, for a conjugate base is equals to this relationship. In fact, take note of this. The denominators, are exactly the same. Okay? So the only thing that is really changing, you can see, is the numerator. All right? And the next slides, and you don't need to memorize these. I just want you to see the process so that you see those equations that I have are not extracted from thin air, they're just very easily derived from systematic treatment of equilibrium. People call it systematic, treatment of equilibrium. All right. And you can see that's what I've just done, to substitute all that. Again, you can see I get in this case what I had before for a monoprotic. And this one you can see is a monoprotic acid. You can see again, for monoprotic base, again, just by following the same process, I get my fractional composition is equals to Ka divided by that. If at all I had a diprotic acid, again, you can see, just follow the process here, you can see that my fractional composition, is equals to that. All right. And if at all I had a conjugate diprotic system or diprotic base, you can see, that my relationship, is actually that. Okay. And so the fractional composition equations, if I can give you sort of the general, sort of equations, they typically look like that. If at all I've got a fully protonated system, the fractional composition of a fully protonated system would be the hydronium ion raised to the number of hydrogens that are present divided by D, and the D is equals to that. You can see if I lose only one proton, now my fractional composition of the first amphiprotic species is equals to Ka1 multiplied by the H plus N minus 1 divided by D. So the D remains exactly the same. All right. And by that, remember, this D really is not a distribution equilibrium, Remember that. It's just a symbol. It's just a symbol in that case. The fully deprotonated system, you're going to see is the fractional composition is equals to the Ka1, Ka2, and so on up to the Kan divided by this relationship. So I hope that's fairly clear. Okay. Again, these ones are Kas, Ka1, Ka2, and so forth. Okay. And that's important, because if you had a problem, that looks like this, okay, where I ask you to calculate, phosphoric acid, and then the first amphiprotic species of phosphoric acid, you can see this one is a triprotic acid, and then the second amphiprotic species, and finally the deprotonated base. Essentially, you can use the fractional composition equations to actually determine those concentrations. All right. And you can see actually it's concentration independent. All right. So the fractional composition, say, of the fully protonated species of phosphoric acid is equals to the H plus raised to power N. And the N, of course, in this case is 3. And that's what I have there. And the D, in this case, the denominator is the H plus raised to power 3 plus the Ka1 H plus raised to power 2 plus the Ka1 Ka2 H plus the Ka1 Ka2 Ka3. The first amphiprotic species, the only thing that changes is the Ka1 multiplied by the H plus to power n, which is n minus 1, sorry, which is 3 minus 1 to give you 2, and so on. Hopefully you guys can see the importance of this. The importance of this is to actually see which is the predominant compound. In what form is a predominant compound at different pH? That's the purpose of doing this. So say at pH of 2, I can determine which is a predominant, compound. And that's why we are using this relationship so that you can determine that. All right? Because assume you swallowed a drug and we know the physiological pH says around 7. So you can determine in what form is that drug inside the body. Is it in its charged form, or is it in its deprotonated, or is it in its neutral form? If it is charged, essentially you're going to be able to excrete it fairly easily. If it's in its neutral form, it's going to get absorbed, into the fatty tissues and so on, because we know the neutral form prefers to be in the fatty tissue. So that's an important, relevant application of these kinds of relationships. And I hope you can see how it relates, to the distribution equilibria or to chromatography, the liquid-liquid extraction, which is what we are talking about here. And so in the next lecture, you're going to talk about very, very briefly then the other different types of chromatographies other than the liquid-liquid extraction, which I've just covered, in the previous slides. And you're going to see that the theory behind the liquid-liquid chromatography is the same theory that is extrapolated into the instrumental based, types of chromatography, such as liquid chromatography, gas chromatography, and so on. And so the next lecture, we're going to talk about chromatography in general.